Hello, everyone. Welcome to our live webcast. Today, we're going to be talking about finding 0 days in IoT devices. So just briefly going to run through some introductions. My name is Nick Cerny. I am a senior security consultant at Bishop Fox, where I primarily work on application security, secure code review, and cloud penetration testing. I also like to hack on embedded devices in my spare time, which is going to be the subject of today's discussion. Before we jump into our webcast, I'm just going to briefly cover our agenda. So we're first going to jump into the IoT security landscape, just going to talk about some emerging trends in the industry and why IoT security is important. Then we're going to talk about the common anatomy of an IoT ecosystem, specifically identifying the common protocols and the targets for exploitation. And then I'm going to talk about building an introductory lab so you have a better idea of what you need to get started. Then I'm going to run through my own testing methodology, or specifically the methodology for hacking embedded devices, so you can replicate it and identify your own real vulnerabilities. And then finally, I'm going to talk about some of the real vulnerabilities I've personally identified based on the practice methodology. And then we're just going to dive into a Q&A at the end. So before we jump into things, I quickly wanted to lead with this quote from Sandworm, which, if you haven't read, is an excellent book about a Russian nation-state hacking group that has regularly targeted critical infrastructure like power grids over the years. So it's clear where the world is going. We're entering a world where every thermostat, every electrical heater, every air conditioner, every power plant, every medical device, every hospital, every traffic light, every automobile will be connected to the internet. Think about what that will mean for the world when those devices become the subject of attack. I wanted to include this quote because I felt that one of the more terrifying premises of the book were the implications of connecting things like our critical infrastructure to the internet using things like industrial IoT devices, which could be the subject of attack. And we have already kind of seen what those implications could be with Sandworm. For instance, they took out several Ukrainian power grids over the years using hacking methods. So now I'm going to talk about the IoT security landscape, where we currently are, and why IoT security matters. So why should we care? Well, it was estimated that the number of connected IoT devices at the end of this year was around 21.1 billion. That number is expected to almost double by 2030. This is also kind of evidenced by the rapid growth in the commercial and consumer IoT spaces, with a surge in low-cost, insecure devices sold on platforms like Amazon or AliExpress. Also, IoT ecosystems are broad and complex attack surfaces that are pretty difficult to secure effectively. And a lot of consumers that buy these devices don't always understand the implications of connecting these devices to their home networks. Some other concerns with these devices include privacy concerns. I've seen instances where these devices will collect a huge amount of data on their consumers unbeknownst to them, and all of that data gets funneled into a remote cloud server somewhere. Another example of a privacy concern was the iBaby hack, which occurred in 2019. This was basically a baby monitoring device that was susceptible to a broken access control vulnerability. So basically, a set of credentials for one user's baby monitor could be used to access any user's data or live camera feeds, which is pretty terrifying. You can also have some potential kinetic effects or real-world effects, depending on what your IoT device is. So IoT devices that can perform physical actions in their environments could also be the subject of attack. Shamelessly plugging my own research from about over a year ago, I performed security research on a Traeger grill, which, for those who don't know, is a smart connected grill that enables you to issue commands to it over the internet, such as adjusting the grill temperature or shutting off the grill, etc. And you can kind of quickly see how IoT security becomes very important, as some of these devices can have dangerous kinetic effects in their environments. Lo and behold, during this particular research, we found an authorization issue that basically enabled us to assume control over other users' grills, unbeknownst to them, and we could successfully issue commands to them. So this can kind of get scary pretty quickly. Going back to industrial IoT devices, where these devices control things like generators and could have disastrous effects depending on the context in which they're used. Mirai is another example of why we should care about IoT security. For those who don't know what Mirai is basically a self-propagating worm, which debuted in 2016 and initially replicated itself, or still replicates itself, by compromising IoT devices like routers or IoT cameras. Mirai is a botnet because all of the devices that it compromises are ultimately controlled by a central command and control server. At its peak, it was comprised of over 600,000 devices, and at the time, it was responsible for the largest distributed denial of service attack of all time, amounting to 1 terabit per second. In its early days, the attack method was very low tech. It involved using a set of 64 default credentials to compromise devices. And in 2016, the source code was also leaked, which led to multiple variants spawning over the years. One of the latest variants, Isuru, shattered the original record with a whopping 29.6 terabits per second, which is nearly 30 times larger than the original record. Most interestingly about this latest variant, most of that traffic stemmed from US-based internet service providers. So that was pretty interesting. Next, I want to talk quickly about the common anatomy of an IoT ecosystem and where the common weaknesses lie. So this is not really meant to be a one-size-fits-all diagram. This is just to illustrate how broad the attack surface can be for an IoT device. So just kind of looking at this diagram here, we have a mobile application. And this mobile application is typically used to facilitate initial account setup, register devices to accounts, and managing end devices. Sometimes managing end devices can occur through an IoT gateway device. But usually the mobile application communicates with end devices or these IoT gateway devices through a protocol like HTTP or MQTT. But oftentimes, as I just mentioned, the mobile application can also connect directly to end devices or an IoT gateway device to facilitate initial setup or things like that. I usually see this happen in where the end device or IoT gateway device will set up a temporary access point and maybe a web server so that the device can connect to the end device and share things like Wi-Fi information so that the end device can ultimately connect to the internet. End devices could be controlled through the cloud, or they're typically controlled through the cloud over a protocol like MQTT or HTTP, or also through an IoT gateway device. If an IoT gateway device is involved, communication could happen device to a device over a protocol like Zigbee or Z-Wave. And for the cloud component, this usually facilitates communication between end devices and the mobile application. So this diagram is just to kind of illustrate that there's a lot of inputs and outputs here that could have potential weaknesses and could be subject to attack. Now we're going to dig into some protocols. This first one is UART, or Universal Asynchronous Receiver Transmitter. This is a serial communication protocol that devices use to communicate, and it does not require a shared clock signal. A clock signal is basically just a signal that helps the two devices communicating determine on the timing of communication. Instead, UART just uses a predetermined baud rate, or simply just a rate of transmission, or rate of data transmission. It's a pretty simple protocol. It involves two wires. which you can kind of see here, or I guess 3 wires. In this case, you would connect the RX or receive pin of device 1 to the transmit or TX pin of device 2. And then vice versa, the transmit pin from device 1 to the receive pin of device 2. And then a ground connection is established between the 2 devices. This is a pretty powerful protocol if you have access to it. It can sometimes be used to gain access or root access to the device and its file system, if there is one. It can also be used to commonly dump firmware or download it. Our next serial protocol is Joint Test Action Group, or JTAG. This is another serial protocol that allows for testing and debugging of connections between chips on a board without needing to physically test probes. This usually involves sending data through or test data through scan chains on the board, which is also known as boundary scan testing. JTAG is a pretty powerful protocol. It can provide us access to, or low-level access to CPU registers and application memory, in addition to peripherals, and can sometimes be used to get root-level access to the device. JTAG can also be used to perform debugging with something like GDB, and also to dump firmware. Serial Peripheral Interface, or SPI, is our last serial protocol that we're going to talk about today. It was developed by Motorola to facilitate short distance communication between microcontrollers and peripherals like flash chips. Firmware and configuration data is very commonly stored in SPI flash chips, which can usually be directly read or modified. So here's an example of one on the right here. You can usually hook onto these little legs here with special clamps or hooks to read data off of them. Or alternatively, you could take the chip completely off the board using a heat gun and perform off-chip data extraction, which I'll demonstrate in a GIF later. Our first kind of data in transit over the network protocol is message queuing telemetry transport, or MQTT. This is a very common protocol in embedded devices, and it's typically used to transmit data over a network. It has some advantages over other protocols like HTTP. For instance, MQTT requires a lot less bandwidth and less power, making it ideal for low power devices. If you've ever dealt with something like SQS or RabbitMQ, it's pretty similar conceptually to this, in that you have a MQTT topic, which a client publishes messages to or subscribes to consume messages from. There are some advantages to using MQTT for unreliable networks or unreliable devices, in that the MQTT broker here in the middle store messages offline, so that if a client can't connect to a broker for a while, they can consume those messages whenever they reconnect. So definitely useful for things like unreliable networks. In this example here, we have a smart thermometer, which can publish a temperature data message to the broker, and then your clients, like the laptop and mobile device, can, which are subscribed to these topics, can consume that data. In this case, the temperature at the thermometer is reading. There's also an encrypted version called MQTTS. There's several other protocols involved in IoT ecosystems. For the sake of time, we're not going to dig into all of these. The important thing to remember here is to not get overwhelmed and to be methodical when you're assessing an IoT device or an IoT ecosystem. The attack surface is pretty rich. You're probably going to find something. And even if you don't, learning is fun. So just have fun with it and don't be afraid to mess anything up. I've actually bricked several devices over the years, including a very expensive Traeger board. So don't worry too hard about it. So now I'm going to talk quickly about building an introductory lab, or specifically what it takes to get started so you can perform your own research. So really quickly here, I just have a picture I took of some devices I use pretty regularly. First one is kind of at the bottom, the Flipper Zero. It's not really a required device, but very useful. There's a GPIO pinout on the top, so it can speak GPIO, amongst other protocols like JTAG, SWD, UART, etc. It also speaks a lot of RF protocols as well, which is very useful. On the right side of the screen, there is a logic analyzer, which is used to decode digital signals. We also have a SOIC clip here on the left side, which is used to interface with those peripherals or flash chips. Then we have a soldering iron here at the bottom, which can be used to solder wires or make physical connections on a printed circuit board. And then there's also an ST-Link here, which can be used to interface with JTAG or SWD on microcontrollers. There's some other stuff not in the picture here that we'll go over in a moment as well. The first one is the multimeter. This is basically the Swiss Army knife of electronic measurements. Multimeters are primarily used to read voltage levels on pins, which can be used for pin identification or debugging. You can also use a multimeter to test for voltage continuity between 2 points, basically to determine if there is a connection there. In the picture on the right, you can see that I used a multimeter to test for continuity between this unidentified debug interface and this system on chip, or specifically an ESP32. An ESP32 is just a very common system on chip in modern IoT devices. And you can see in the multimeter here that there's 100 ohms of resistance. And the reason for the resistance was due to a resistor that was on the back of the board, which explains that. But there was a connection here demonstrated by the continuity mode of the multimeter. These can run $10 to $100. So really depends on how fancy of a multimeter you get. You also have debug adapters. So these can be used to establish a physical connection to the device. Could be used to dump firmware, gain root access to the device, or perform debugging, depending on the context and the debug interface is exposed. Assuming you can make a connection, JTAG and SWD adapters can give you intricate control of the CPU of the embedded device, which is pretty cool. You can do stuff like halt the CPU, debug programs with GDB, etc. These are pretty cheap. I have one of these. I got it for like $10. So pretty cheap to get on Amazon. Soldering iron. So this is a pretty common tool that should be in your toolbox. This is used to make connections or tap into signals on a circuit board that otherwise wouldn't be accessed by your typical consumer. As chips get smaller and smaller, I would even recommend using a micro soldering iron as opposed to a regular one, or specifically a soldering iron with finer tips to allow for more precision with your soldering. These are also pretty cheap, but micro soldering irons might be a little bit more expensive. Here's the logic analyzer. This was also in our screenshot, or I guess picture earlier. Logic analyzers are used to reverse engineer digital signals on a printed circuit board. This is a pretty neat little device. It can be used to capture and decode various signals, or I guess signals from protocols like UART, SPI, I2C, and other digital signals. And I actually had the one listed in that screenshot as well. But here is the logic analyzer in use. This is specifically Logic 2, which is Saley's software. This can be used to decode digital signals, as I just covered. But basically, there are several channels here that kind of correspond to the physical connections on the logic analyzer itself, or the connections you made to those pins. And the horizontal axis here is time, and the vertical axis here is basically representing logic changes, or specifically voltage fluctuations between high and low voltages. In this particular screenshot, this shows a captured UART signal that has been decoded by the UART analyzer, and you can actually see the message that we're receiving here from the MQTT client, or the log that's being transmitted to the UART interface, saying that the client was not connected. So pretty cool and very useful if you're trying to decode a digital signal or figure out what's being transmitted. Pretty self-explanatory, but a lot of IoT devices come with an Android application or an iOS app to control them. So having a cheap unlocked Android device is pretty useful. You could also use something like Android Studio, but there are some limitations with Android Studio, specifically hardware limitations, which is why I recommend just getting a real device. For example, on some recent research I did, the Android application required real Wi-Fi access to set up the device and scan for nearby access points, and that wasn't supported by Android Studio. So having a real Android device for the purposes of security testing is very useful. This is kind of my first honorable mention, meaning you don't really need this. I just like it as a product, and it's pretty useful to have around. For those who are not familiar, this is the Flipper Zero, which has kind of been coined as the pen tester multi-tool. I found it very useful for IoT stuff, actually, as it speaks several different protocols, like RF protocols. It also has a pinout on the top here, which you can see I'm utilizing. And it speaks GPIO, UART, JTAG, SWD, SPI, and more. This is a bit expensive, so if you don't want to spend that kind of money on a Flipper Zero, you don't need to actually. You can go with a $10 debug adapter, but again, just kind of a cool product. But here I'm using it to extract the firmware from this device over UART. This is another honorable mention, meaning not required, but having one of these makes things like microsoldering much easier. The one I have on the screen is the one I have. It basically lets you hook up the digital microscope to a monitor, which makes soldering very easy, as you can see exactly what you're touching with your soldering iron. That would otherwise be pretty difficult to see with the naked eye. Last honorable mention, a heat gun. You can use this to desolder and remove chips from the board. One common application of this is to perform off-chip firmware extraction. So not required, but useful. So testing methodology. How do we identify vulnerabilities, or how do we go about finding them? Just like with all other types of testing that we do, you kind of want to begin by developing an attack surface map, or simply just gathering as much information as you can about whatever device you're testing. Specifically, you want to identify all the possible paths of exploitation or potential paths of exploitation. Typically, I like to start by reading device public documentation and trying to identify all the potential inputs and outputs to a device. I also like to ask myself some questions while I develop the attack surface map. Specifically, identifying what RF protocols the device speaks, how it connects to the cloud, and how it's ultimately controlled by our mobile device. We also want to find out if the application ever connects directly to the device over some sort of wireless protocol, like Wi-Fi or Bluetooth. And we want to identify how the device receives firmware updates, and if any of these communications can be tampered with or misused. Also pretty important, whenever you're dealing with a device with RF capabilities and you are selling in the United States, you need to publicly file with the FCC or the Federal Communications Commission. So this is pretty useful for hackers like us, because we can use this documentation to gather a lot of information about the product. For example, FCC reports can contain internal photos of the device, external photos of the device, RF test reports, etc. All of these are extremely useful when we're trying to identify a device's capabilities. So here's some internal photos from an FCC report, specifically an FCC report that I looked at when I was testing a smart lock. So yeah, you can see that it's very useful to look at these because you can look at what a device looks like on the inside without even having to purchase it at first. In this case, the smart lock used a LoRaWAN antenna to communicate back to a smart hub or an IoT gateway device. And you can see the LoRaWAN antenna is marked here. So this is all very useful information for us. So here's a practical attack surface map example I developed for my Traeger research that I performed over a year ago. Here you can kind of see all the potential inputs and outputs to the grill that could be subject to attack. So first and foremost, the grill featured Bluetooth and Wi-Fi capabilities. It could connect directly to the mobile application to facilitate initial setup using a temporary access point and an HTTP server. After the setup was completed, the phone issued commands to it over MQTT through the MQTT broker in the cloud, and the grill would receive those commands through the topic that it was subscribed to. Some of the commands that the mobile device could issue were temperature adjustment commands, like changing the temperature of the grill or shutting it off, etc. The grill could also communicate its current status to the mobile device over MQTT as well. The grill also featured Bluetooth capabilities for the meat probe accessories that you could get with the grill. So these are all just examples of things that should be scrutinized and potential avenues of attack that we should make note of. So analyzing the mobile application. This is where I usually like to start when performing research. It's pretty trivial to use your mobile device or Android Studio to download and extract the Android package kit or APK. APKs can be decompiled pretty easily using JADX, which is an open source tool. And when you're analyzing the mobile application, it helps to proxy the Android device through something like Burp Suite or Zap Proxy, so you can review the communications that are happening from the mobile application to the whatever device you're testing. Sometimes this might require bypassing TLS certificate pinning, but usually this is pretty easy to hook and bypass with Frida. Next, I like to analyze the end device or whatever device we're looking at. This typically means physically taking the device apart and identifying the chips on the board. Some of these chips have great documentation associated with them, which can help with pin identification, or it can just generally tell you if there's any debug interfaces associated, etc. The chip on the right is a picture I took with my digital microscope. This is an Atmega 88PA microcontroller, which was present on the Traeger grill printed circuit board. So this kind of shows how useful a digital microscope can be, because this otherwise would be pretty hard to read. I mean, it still is kind of hard to read, but with a naked eye, it would be even more difficult. But after cross-referencing this ID that's engraved on the chip with some online documentation, you could determine that this chip was likely used to interface with temperature sensors on the board or other components like the auger motor. But yeah, just kind of an example of how quickly and easily you can identify a chip and cross-reference what the ID is and determine what it's doing in the context of your particular device. So this slide is purely just for reference. So this was the Atmega chip that I just talked about. So you can definitely see how having a digital microscope is pretty useful when you're trying to read the very small engravings on these chips that would otherwise be pretty difficult to see. Here's the pinout for a different chip, specifically the ESP32W room. This is a system on chip that was present on a device that I most recently performed research on. This is just kind of an example of how some chip manufacturers, in this case Espressive, have some pretty extensive documentation for developers on pinouts, which is very useful for hackers like us. For example, you can see exactly where the UART pins are on this chip, which is right here. Also, there's a GPIO pin, which we can hold to ground, GPIO 0 pin, which we can hold to ground, which can be used to force the ESP32 bootloader into different modes. ESP32 pins are relatively large and easy to solder to, as you can see here, especially if we have a micro soldering iron. And I've yet to see one of these with firmware protections, so it's usually pretty easy to get the firmware off of these devices. The picture on the right is to just kind of show you how large the pins are and how they can easily be soldered to extract the firmware. So sorry in advance for the poor quality GIF here. This GIF is just to demonstrate off-chip firmware extraction. So here I physically took the chip off the board and I put it in this universal programmer. And you can use this universal programmer to dump the firmware of the device. Sorry, the GIF is a little bit small here. But here we're reading the firmware off the device, and then you can just download it that way. I definitely did not need to do it this way, as it was easier to actually get the firmware over UART, but this is just to demonstrate another method of getting it off of the device. And you can get the firmware a variety of ways. You could use a physical connection like UART or JTAG, or you could download the firmware directly from the internet or a remote API if you discover where it's being stored. You could also man in the middle of the firmware if it's possible during a device update. Once we've extracted the firmware, we need to analyze it. So I usually like to start by reviewing the actual strings that are in the firmware image. This can be accomplished with the strings command or XXD, depending on your preferences. Strings can give us a lot of context when we begin to analyze the code in Ghidra or whatever your preferred analyzer is. Here we've grabbed the partitions table from the ESP32 image, which starts at the hex 8000 offset. And this is kind of like a unique partition table in ESP32 images that tell you what the various parts of the firmware are that could be parsed out for further analysis. So once we have acquired the firmware, we need to reverse engineer it. You can use a tool like Ghidra, IdaPro, or Binary Ninja for this purpose. Before popping the firmware into Ghidra, we need to make sure that we select the right decompiler settings. In this case, this was an image on Extensa architecture. So we had to reflect those settings in the Ghidra settings. We can see here some pseudo C, and we can see that we were likely dealing with some sort of function that was responsible for initializing the MQTT client. Specifically, you can see some string formatting kind of happening here, and the MQTT topics that the device was subscribing to. And you can also see that the ID of the device was used to kind of construct the device topics. So now that we have a fundamental understanding of kind of what our methodology should be for looking at an IoT device, we can kind of see what the impact is when we practice a said methodology by looking at some real vulnerabilities that we have identified in the past couple of years. So I recently performed some research on a smart hub, or specifically an IoT gateway device produced by a company called YoSmart, which you might not have heard of. This research produced a number of vulnerabilities, with the two most glaring issues being insufficient authorization controls and unencrypted communications. There was also some data leakage that was occurring on the APIs that could that kind of disclose exactly where customers were located down to the geographical coordinates, which is kind of scary. So you can kind of see in a moment why this made the issue of authorization extra bad. So YoSmart produced a whole suite of smart devices that communicates back to their YoLink hub. Devices communicated back to the smart hub over a protocol called LoRaWAN, which is a wireless protocol. LoRaWAN is basically just a low power, long distance protocol that's also encrypted. The somewhat ironic thing here was that when I performed this research, there was an encrypted protocol used for the device-to-device communication, but the hub-to-cloud communication was fully unencrypted. All of the communication to end devices goes through the device hub here. So it was kind of a single point of failure and a good target for our research. Ultimately, there was a lot to look at here as potential avenues of attack. Before we dig into the meat and potatoes, I just wanted to quickly cover the terms of service for YoLink devices, which I thought was pretty interesting. So it says here that you understand that your content, not including credit card information, may be transferred unencrypted and involve transmissions over various networks. So I thought this was kind of an interesting bit in the terms of service because I don't think a lot of people actually read the terms of service when buying these devices. So they might not have caught this. So as we just covered in the testing methodology section, one of the most important objectives should be to recover the firmware. With enough time, effort, and patience, we can reverse engineer firmware images and gain a pretty good understanding of how the device works and if there's potential vulnerabilities. Here I used the Flipper Zero to extract the firmware from the device after making the appropriate UART connections. Again, this is not a required device. You could simply use a $5 debug adapter on Amazon and achieve the same results. I just thought the Flipper Zero was a pretty cool product. And one of the cool things about the Flipper Zero also is you can literally see the amount of bits that are transmitted and received over the wire on the kind of display here, which is pretty cool. And on the right side of the screen here, there's kind of another angle of the UART connection we're making. I literally used sewing needles to make connections to the debug pins, which just goes to show that sometimes the dumbest solutions are also the best solutions with the tools you have available. So once we had made a UART connection to the ESP32, we were able to view the bootloader logs as well as the application logs. So here you can see that the bootloader is being loaded at the very top here, and then a bunch of application logs related to my MQTT connection, my device ID, etc. Specifically, one of the first things that jumped out to me was this configuration URL that was being logged, which points to the YoSmart API. And one thing you'll notice is that it kind of follows a particular format. You have this PF here, followed by my device ID, and then this seemingly arbitrary MD5 hash. And after the device visits this URL, you can see that our MQTT credentials are getting logged or transmitted to UART as well. So we can kind of infer from that that the device is visiting this URL and getting its own MQTT credentials. So based on this, you can kind of see some red flags start to emerge in where the potential vulnerabilities lie. Like, for instance, where does this MD5 hash come from? You might suspect that it's calculated by the device somehow. And we could ask ourselves, like, could we calculate that MD5 hash ourselves? Could we use it to calculate other users' MD5 hashes and get their device credentials? Another interesting thing here as well is this device ID seems to be derived from the MAC address, which is also transmitted to UART here. So these are interesting things to take note of and could lead to some interesting vulnerabilities. So after visiting that URL that was logged, our inference was correct. We could see MQTT connection information, as well as a LoRaWAN configuration. So here you can see our device ID, the URL for the MQTT broker, and our password, amongst other things. So after we identified what that URL was and what its purpose was, we wanted to determine if we could actually calculate those URLs that belonged to other user accounts or other user device hubs specifically. So first I wanted to identify how the device hub was calculating the MD5 hash. After popping the firmware image into Ghidra, we saw some interesting function calls. Specifically in this function, we could see that there was some space being allocated on the stack here, followed by a call to the get device ID function, which I'd renamed earlier. And then we see these two function calls here. We see likely the string concatenation function right here, which takes in our device ID, as well as this baked in string in the firmware, which seemed to be another arbitrary value. And then after the string concatenation took place, this was stored in one of the stack buffers that were allocated. And then this other function call seemed to take in that stack buffer and store whatever result into another stack buffer. So given that the final value in the REST endpoint appeared to be an MD5 hash, we could check if this concatenated string produces the secret value that's used to protect our own device's credentials using a tool like MD5Sum. So recall that when we visited this endpoint, the URL was constructed using our device ID followed by this kind of MD5 hash value where the first 2 bytes began with 10-0B. So when we echoed our device ID concatenated to this value that was in the firmware and piped it to MD5Sum, you can see that the result is a direct match, meaning that our inference was correct. So basically what this means is that just by knowing other users' device IDs, we could retrieve their device's MQTT credentials because we could calculate that secret MD5 hash in the final part of the REST endpoint. With the MQTT credentials that the device used, we could do a number of things. We could disrupt active MQTT connections. We could intercept Wi-Fi credentials that were sent by mobile clients. We could also transmit inaccurate data to the MQTT broker on topics that are used to reflect the device's status, etc. And to demonstrate this, I used an MQTT client in my terminal and subscribed to the MQTT broker using my own device's credentials. And then for my mobile device, I issued a password or Wi-Fi password change request. And you can see that we captured the SSID and password of our own Wi-Fi network. Here's where it gets a lot worse. It turns out that the MQTT broker did not enforce authorization controls for mobile application sessions at all. Meaning that once we had any other user's device IDs, we could issue commands to them using our own authentication session. To carry out that type of attack, we would need a few things. Specifically, as I just mentioned, we would need the user's device ID. We would also need a family ID of our own attacker account, which was basically just some UUID that you could get when you logged in. We would also need a valid authentication token and a valid command. To make matters somewhat worse, the device IDs could be predicted, or at least they seem to be sequentially generated. Or just backing up a little bit, the first 3 bytes here corresponded to the OUI of the manufacturer of the device, which I believe was King Ting. This middle value here seemed to correspond to the device we were targeting. In this case, the device hub. That seemed to be some sort of ID to differentiate between the different YoSmart devices. And the final 3 bytes here were the ones that were sequentially generated or appeared to be sequentially generated. And because those final 3 bytes were sequentially generated, we could iterate through them to identify other user devices. So yeah, that definitely made matters a little bit worse. Okay, so here's kind of our attack scenario. So for instance, we have our 2 accounts here. We have an attacker account and a regular user account. And the attack scenario is going to involve an attacker attempting to publish a command to the victim's Yolink hub while still authenticated as the attacker. So as I mentioned before, the attacker simply just needs a valid session and their own family ID, which can easily be retrieved from their account. Then they could issue a command to unlock the smart lock in the victim account by publishing to its MQTT topic, which the user's Yolink hub is subscribed to. The MQTT message will then be consumed by the user's smart hub, and then it will transmit a LoRaWAN packet to the smart lock and unlock the lock. So I didn't trust the demigods, and I have pre-recorded this attack for you. This shows me grabbing a valid session, or basically the family ID and the authentication token, and then pasting that in the MQTT command here. And then we can copy this out into our terminal. And once the command has executed, it would be received by the smart lock and the lock unlocked, as you just saw. So that was the attack. Pretty scary when you consider the implications. If I was a criminal, I could literally gain access to whatever was being secured with the smart lock. And just considering another one of YoSmart's devices, a smart plug, we could use this vulnerability or issue of authorization to toggle the power state of devices connected to the smart plug, which could have a variety of impacts depending on what's connected to it. So here was kind of a timeline representing our responsible disclosure process with YoSmart. We discovered the vulnerability back in mid-May, or the vulnerabilities, and then we disclosed a month later via email with the report attached. We then followed up with a physical letter after no response, a few days, or I guess more or less a week later. And UPS confirms the letter was received by YoSmart. After we didn't receive a response, we followed up with a phone call to the support line to request an update. But ultimately, we did not receive an update until we went live with our disclosure on October 2nd. And then on October 10th, YoSmart released their own statement addressing the vulnerabilities. And although we didn't really collaborate on remediation efforts, YoSmart claimed to have fixed the vulnerabilities, which is pretty cool to see. According to YoSmart, the authorization flaw that we just saw was due to a bug in the server's internal caching system. The firmware was also updated to not use that sort of static credential that we saw that was baked in the firmware in the authentication process to retrieve device credentials. And then finally, the firmware and mobile application appear to be updated to use encrypted communications. So overall, it was pretty cool to see that YoSmart made an effort to address these vulnerabilities to protect end consumers. This was basically just an honorable mention of some prior research that I've done. The TLDR of it was that the Traeger girls suffered from a similar authorization issue, which I touched on a little bit earlier. You could basically misuse the Traeger APIs to register other user grills as your own and effectively assume control. From there, you could issue commands to the grill, such as changing the temperature or turning it off. In this case, I used it to burn my colleague's tofu by setting the temperature to 500 degrees, which is why you can see all the smoke in the picture here. Unfortunately, or maybe fortunately, there was not a way to remotely start the grills due to a safety feature. But one thing I've always kind of been curious about was whether it would have been possible to start the grill remotely using some kind of binary exploitation magic. That's kind of an area I'm currently exploring, but I have no idea how the Extensa architecture works, so I'll have to dig deeper on that. Before I head into some Q&A, I just want to leave you with some closing remarks. The first one here is that practice makes perfect. Sooner or later, you're going to brick a device, and that's okay. I've bricked many devices already, so practice makes perfect. Practice on cheap devices. You can literally go to your local Goodwill and find a crappy smart device for under $10, and these are perfect targets to practice on. And lastly, there's something here for everyone. If you're into binary exploitation, web or mobile application exploitation, reverse engineering, cryptography, or other things, you'll likely find something that you're interested in, and you will likely enjoy hacking embedded devices. And one of my favorite aspects of doing this kind of research is the tangibility of it. Being able to physically tear down a device and see how it works is very fun. And with that, we can jump into some questions. So just quickly looking at the questions in the chat here, I'm just going to start off with the first one, which is asking, so like, how do you find vulnerable devices on your network? And I think it's not really much different from how you would typically find vulnerable devices on a network. You can kind of use your standard network scanning tools like Nmap to perform like a ping sweep or something to identify devices on your network. Your router will also tell you what devices are currently connected via the administrative interface. But if you're more worried about devices being actively exploited on your home network, you can set up a network monitoring tool like Wireshark and maybe monitor for any suspicious patterns that aren't normal for your IoT device or maybe a bit anomalous. For instance, maybe like traffic spikes or any weird connections to IP addresses or domains that it doesn't typically make. Also, I definitely recommend segmenting your network from your normal daily devices like your laptop and stuff. Having an IoT network separated from your normal stuff is always a good idea. And I think another solution to address it, if you're worried about devices being actively exploited on your network, is something like a Pi-hole, which is basically a DNS sinkhole that runs on a Raspberry Pi. You can use a sinkhole or a DNS sinkhole to log weird domains being visited by your IoT devices and even block unwanted domains. So I guess I hope that answers your question. The second question was if we have any upcoming workshops for, I guess, hacking on embedded devices and IoT devices. And the short answer is that we don't currently have one planned, but if we do plan one, we're probably going to announce it first on our Discord. So I know Sean just dropped a link in the chat there, so definitely join our Discord if you're not already on there. An announcement will be posted there. There's also a deep link on our website for our Discord. So yeah, we don't currently have one planned, but that's something we're looking into. The third question, it looks like they were asking if we shared the findings with YoSmart. Yes, I believe this question was asked actually before we put up the disclosure timeline slide. But yeah, we got in contact with them, and once they acknowledged the issues, they were actually pretty responsive and addressed them almost immediately. So it was cool to see that they were addressing the vulnerabilities as soon as they could. Looks like we have another question here. how is that MQTT protocol working? Is that YoSmart domain a local server? So that domain actually was pointing to a remote MQTT server or broker. And basically the way it works, I touched a little bit on this earlier, but the way the MQTT protocol works is it works on a publish and subscribe basis. So basically you have this broker that kind of sits as an intermediary server between multiple clients. In this case, using the YoLink hub as an example, the YoLink hub would subscribe to topics on the MQTT broker, consume messages from those topics, and also publish messages to those topics. The mobile application would work similarly. It would publish messages to topics. Those messages would ultimately be consumed by the YoLink hub and vice versa. I hope that answers your question. Looks like we have our last question here. How was the communication with YoSmart? To me, outside bounty platforms consider me a bad actor and they feel threatened. Yeah, this is actually a great question. I was a little bit worried about this myself. I feel like typically when you approach a company that doesn't have a active bug bounty program, your response can be somewhat mixed depending on who you talk to. Fortunately, YoSmart was pretty receptive to the findings, but that was definitely something I was concerned about. Ultimately, if they're not happy with your findings and they consider you a bad actor, as long as you follow the responsible disclosure process, you can't be held, or you shouldn't worry about legal consequences, as long as you didn't do anything nefarious, obviously. But yeah, I mean, if they're not receptive to your findings, that's ultimately their problem. You're doing your work as a bug bounty researcher, and you shouldn't have to worry about that as long as you're following the correct processes. That looks like all of our questions. It looks like we had one more pop through. Did you approach them from Bishop Fox perspective or personal? Yeah, we definitely used the Bishop Fox name. I sent them an email using my Bishop Fox account. Similarly, when we sent them a physical letter, we let them know that it was from us as well. But I mean, you don't really necessarily need a reputable name to do this kind of research. It's as long as you're following the responsible disclosure process, you shouldn't have any real problems. So I wouldn't worry too much about being associated with the Bishop Fox name or Google or whatever. Yeah, so don't worry too much about that. But yeah, if you have any additional questions about, I guess, the responsible disclosure process or anything else covered in this presentation, I'd be happy to cover that in the RedSec Discord. So definitely pop over there if you haven't already. But yeah, thanks for all the great questions. I appreciate it.